Welcome to Math 119, where we're talking about polynomial functions. So first, we're going to be starting off with talking about zeros, then we'll go into some end behavior before we start to actually graph these polynomial functions. So zeros of polynomial functions are the x-intercepts of the graph of the polynomial. Thus, when we're asked for us to make an equation of the polynomial function, we can use these solutions of the polynomial. So previously, right back in chapter 1.3, we learned how to factor. 1.8, we learned how to solve. When we go to solve, we're actually getting set up for this point right here, where we're going to factor the polynomial, solve it, so find your x-intercepts, your solutions, and then we get to graph those solutions. So we originally start with this expanded form of your polynomial, where we have your leading coefficient right here. Now, this is a polynomial in standard form or expanded form, where we have your a sub n. This is just a fancy way to say this is your leading coefficient. And earlier we talked about your leading coefficient being attached to the highest degree. And so when we were talking about ordering these polynomials way back when, we wanted to make sure your degree, that the term with the highest degree came out in front. That is because your leading coefficient and your degree are working together to give us a big picture as to what your graph is going to look like. We also talked about back in chapter 4.1, where we learned about transformations. And if our leading coefficient is positive or negative, will allow us to either have an up or a reflection over the x or y axis. Now, another key bit of information when it's in this form is this a sub 0. This is your y-intercept. Excuse me. So these are the only important bits of your polynomial in this form that we can kind of gather. So the leading coefficient telling us the direction, the highest degree telling us the shape, and then your y-intercept being, well, where exactly are we touching your y-axis? So it says the degree of the polynomial is the variable with the highest exponent. Directly attached to this is the leading coefficient. Now, typically this comes out in front because of the proper notation of polynomials, something we just talked about. Sometimes if I'm trying to figure out, do you know what the highest degree is, I might tuck this into somewhere in the polynomial itself to see, can you actually pick it out? So giving example 1, can you find the degree and leading coefficient of the polynomial? So see if you can pause the video, put it into proper notation, and then answer the following few questions. Proper notation, we are just rewriting your expression. So we have p of x. In your highest degree here, we go from 3 to 5 to 1, meaning that we have negative 3x to the 5th coming out first because it's the biggest degree. Then the next highest is plus 6x cubed minus 2x squared plus x minus 7. So now that we have it reordered, what is your leading term? Well, the leading term is this first term right here, negative 3x to the 5th. Therefore, what is your degree? The degree is your 5, that is your exponent. And your leading coefficient is the numerical value of the term, this being negative 3. So knowing what you know about polynomials, that is from chapter 3.4, where we talked about kind of recognizing what these graphs are going to do as far as a pattern. Can you determine the degree and the direction, or the shape and the direction? With it being an x to the fifth graph, we're this S-shaped curve, but us having a negative leading coefficient, we're going to be a downward spacing S shape. Now, getting an idea for what these graphs look like beforehand is a really good exercise because it allows us to compare your end graph with what you originally thought. Now, if those two don't match, then obviously something is a little bit wrong. Now, because we talk about polynomials and functions, and we're going to be starting to graph a couple more complicated ones, we might see in the future, especially in your calculus classes, where we might not have a continuous function. In your function, as you go to graph, some might have a break. So this being a break, it literally goes from one point and it jumps and it breaks and it goes up to another. You might have a hole in your graph where it doesn't actually break, but there is a small portion of it that now has a specific hole. We have a cusp and a corner. I can never get the corner one. Cusp and corner. It's best I can draw it. Excuse me. So all of these examples, if you see any of these few that might happen in not the ones that we're going to be graphing today, but in the future in your calculus classes, these would be considered discontinuous. In other words, these are not continuous functions. Continuous functions, meaning there's no breaks, there's no holes, there's no cusps or corners. The graph is nice and smooth and fluid. You don't have to pick up your pencil. It's nice and smooth, so you're not making any sort of jagged edges. The ones that we will be graphing for chapter 5.1 will all be nice and smooth and continuous. When we start to graph your rational functions, so chapter 5.5, we'll talk about where we actually don't have a continuous function. We're still graphing nice smooth lines though. At times we could have a hole as well. So now your end behavior of f of x, as x approaches either infinity or negative infinity. So what does, and this means, what does your y do as x goes to infinity? So the notation for that, it's just saying as f of x, as x goes to infinity, this is just saying, well, if x we know to go to infinity, what is your f of x? What is your y value doing? Now, your y value can do a number of things, and this all comes down to the behavior. It's something called your end behavior, which we take your degree and the leading coefficient. The degree tells us the shape. So that's why from your above exercise, we were talking about your degree here. Well, we said a degree of 5, or either this S-shaped curve, right, going up or down. And then the leading coefficient, we said, oh, it's -3, therefore it's an x-axis reflection. We're going to be going down. So this tells us the direction. So as we're going through, right, we might have a various, we might have 4 different types of end behavior. So one is if the degree is positive, or if the degree is, actually, hold on, before I actually get to that, let's do the ones that we have graphed before. So far we have graphed a line and we have graphed a parabola. So let's say your degree, right? What is the degree of your line? Well, the degree of your line is 1. And let's say in our case, for our purpose, the leading coefficient is positive, right? Keep in mind, this means y equals mx plus b, where m is positive. So what kind of line is going to, what kind of line will that give us? Well, that's going to be a positive line because your slope is positive. So we're going to be going like this. So your end behavior in this case, what is x doing? What is y doing as x goes to negative infinity? Well, if this is a graph, right? Negative infinity for your x values is over here. So what is your y value doing? You notice that as we're continuing to go towards the negative side of your x values, this graph, this line is telling us that your y values are going down. So anytime that your y values go down, we are going towards negative infinity. So we can say y goes to negative infinity. So if it's a down arrow, it's negative infinity. Whereas if we say, well, x, if it goes to positive infinity, what is your y value doing? So again, this just being a grid, well, x goes to positive infinity over on the right-hand side, what is your y value doing? Well, your y values are continuing to grow upwards towards positive infinity. So anytime we have an upwards facing arrow, y is going to go to positive infinity. Now let's do these again with your other lines and your parabolas. So again, we're talking about a line with a negative slope. So that means your degree is 1, your leading coefficient is negative. Now, can you draw a line that with a negative slope? So that's going to be downward facing. Therefore, what is x doing? Or sorry, what is y doing as x goes to negative infinity? Well, as we go to negative infinity, x value in negative infinity is over here on the left-hand side. Your y value is continuing to go up towards positive infinity. So again, we have an upwards arrow, y goes positive infinity. And what about on the other side? As x goes to positive infinity, what is your y value doing? Well, y is going down towards negative infinity. Now this, what we're doing is called arrow notation. It's kind of getting us set up in the future to talk about limits. Now let's look at parabolas. Can you draw a parabola going up? So an open facing parabola. What does the degree, what is the degree on your parabola? Well, degree would be 2. We're talking about quadratics. And for us to go up, that means your leading coefficient here is positive. So let's evaluate as x goes to negative infinity and x goes to positive infinity. What are your y values doing? Well, towards negative infinity, the left-hand side of my graph is going to go up. And towards positive infinity, the right-hand side of my graph, my x value is also going up. Both of these ups suggest that your y value goes to positive infinity. Now let's see if you can pause the video and try where the parabola is going down. Parabola is going down. So we're at a concave down graph. We're degree of 2. We're still talking about polynomials here, or the quadratic here. Leading coefficient in order to go down is negative. So let's evaluate. As x goes to negative infinity and positive infinity, your y values are both going down. Now, the nice thing about these 4, if you can remember these 4 end behavior, when it comes to any polynomial, it will take on one of these 4 types. So if we were to build a quick chart to kind of illustrate that one more time, right, we could talk about this end behavior chart. Eventually, you will not need this chart whatsoever, right? But we can have odd degree. So numbers like 1, 3, 5, and these are all on polynomials. X to the first, x to the third, x to the fifth. We got lines. We got S-shaped curves, right? But keep in mind, your line was both positive and negative. So we could have 2 types of orientations. That in which we have a positive leading coefficient, or that with a negative leading coefficient. So if it's a negative leading coefficient, right, we're just a line facing down, or we're an S-shaped down. With a positive slope, right, positive leading coefficient, we're a line that goes up, or an S shape that goes up. This is where it's handy when you have understand and took away from the 3.4 lecture that we don't have to memorize these graphs. We can just memorize the pattern. Odd degree. Now we just pair it with either a positive or a negative leading coefficient. So odd degree will either go down or we're aligned. Therefore, as x goes to negative infinity, your y value, right, negative infinity is going down here. Your y value is also going to go to negative infinity. As x goes to positive infinity, y goes to positive infinity. And we can do the same for the other side. As x goes to negative infinity and positive infinity, negative infinity, we go up on both of your graphs. So y goes up towards positive, and the reverse, as x gets more and more negative, or sorry, as x gets more and more positive, y gets more and more negative. We are going down on these graphs. Now, if we're not an odd degree, we are therefore an even degree. Things like x squared, x to the fourth, x to the sixth, right? So we're either these U-shaped graphs with a positive leading coefficient, or what we'll be seeing is this like W shape at times. Or if we have a negative leading coefficient, we're going to be concave down, or again, a little W-ish shape. But when we are a leading coefficient, right, as x goes to negative infinity, both of her sides will also go to positive infinity. So as x goes to positive infinity, your y value will also go to positive infinity. So your shape, right, we talked about 3.4. What was the pattern? Well, we said when it's an even degree, the direction is both the exact same direction, whereas the odd degrees are going in opposite directions. So your y values here should go in the same direction. Now, if it's a negative leading coefficient, that means it is flipped downwards. So again, these directions, they're all going down. So y goes to negative infinity for both. Now, if this chart helps, that's great. But just think about it. What would you do if it was a line or a parabola? Things that we've done before. So let's determine your end behavior and write it in the arrow notation. So we're taking one of these, and you only have 4 cases. They're not going to change. So it says determine the end behavior. So for example, A, looking at your polynomial, right? There's 2 things that we need to pick out. That being your degree. Your degree here, the highest degree we have is 4. And your leading coefficient, that being -2. Because it's negative, right, we have a change in the direction. Degree, right, with it being 4, we're going to be this U shape, whether it's up or down. That's your shape. And now with us having a negative leading coefficient, that's going to tell us that we're not this concave up shape. Instead, we're now going to be concave down. This is like the most basic idea, because this complicated graph won't look like a parabola. Instead, it'll have lots of waves to it. So if we're writing an arrow notation, both of these arrows are suggesting that your y values are going towards negative infinity. I should put that right here. So as x goes to negative infinity, your y is going to negative infinity. And as x goes to positive infinity, your y is going to negative infinity. So see if you can try B. So your degree here is 5. Your leading coefficient is 3, so it's positive, right? 5 suggests we are this S-shaped curve. Your leading coefficient is positive, meaning that we have a S going up, meaning that one arm is going down towards negative infinity, one arm is going up towards positive infinity. To the right-hand side, we have X goes to negative infinity, Y goes to negative infinity. And as X goes to positive infinity, Y is going to positive infinity. The more practice that you get, the easier this will come. Again, this really comes from understanding the patterns that your graphs have. So you might need to go back to 3.4 to talk about patterns. Now, real zeros, right? Zeros are solutions, are x-intercepts of your graph. So what we do is when we have it in this nice factored form, x minus c is called a factor. Whereas once we actually set it equal to 0, right? We spent all that time in chapter 1.3 to say, hey, can you factor? And then in chapter 1.8, we said, hey, can you solve? When we solved, we finally got a solution. So when x is equal to something, you have a solution. Therefore, c is your 0 of your graph, or of p of x, your function. And again, because it's a 0, it's called your x-intercept of the graph. So we should have the coordinate c comma 0 on your graph. This is where your y value is always 0 on your x-intercept. And c is that solution. So now we'll have lots of different types of polynomials. You might see it still in a quadratic. You might see it in a cubic, a quartic. We won't get so heavily in depth where we graph things that are not going to be factorable. So for us, they're all going to be factorable in one case or another. Or their graphs are just going to be simply easily transformed or translated in order to be graphed. So the first thing we want to do is set it up into this portion. So if it's already in factored form, so you have parentheses, you have x plus or minus this sort of number. When it's in this form, we go step 1, we set p of x equal to 0 because this is your y, your x-intercept, right? Your x-intercept, y goes to 0. So we set p of x equal to 0. Step 2, we factor. That is, if it's not factored already, in this form, it would be factored, so we can skip those steps. And then step 3, we're going to set your factors equal to 0 and solve. Now, one last thing before I move on. If you have a degree on any sort of your parentheses, this is called your multiplicity. This multiplicity is there because it'll tell us, depending on the 0 itself and the degree itself, you might have a bounce, a slide, or a pass. So with your multiplicity, if it is an even degree, we bounce. If it is an odd degree, other than 1, we slide. And if it is a degree of 1, we pass. And when we're talking about we bounce, we slide, we pass, this is all over the x axis. And we're going to be seeing what happens there to start. So can you, for right now, in example 3, can you find your zeros of the function? We'll get set up to graph these, but we won't actually graph them in full. I just want us to get practice finding your zeros of your graph. So that being, set it equal to 0, factor, set your factors equal to 0. So pause the video here and see what you can come up with. So with this being in factored form, we can set p of x equal to 0. We don't have to do any sort of the work. We don't want to expand it and make it bigger and look like this, because then we have to go back and factor. Instead, we get to set both of your parentheses equal to 0 and solve. So we can add 2 to the other side, subtract 3 to the other side, and x is equal to 2, and x is equal to -3. But we said, hey, these x values, right, they are zeros. They are your x-intercepts. So as a coordinate, we have 2, 0. Always 0, because this is set equal to 0. This is your y. P of x is just another way to say y. And same thing here. -3, 0. This is another x-intercept. So if we were going to graph it on your graph, let's say this is your y-axis. We have 1, 2, 3. So this is where your x-intercept would lie, 2, 0. 1, 2, 3, 4. And this is where another 0 would be on your graph. Now we talked a second ago about multiplicities. Your multiplicities, if you were to have them, would be located right here. Now notice, because there's no number showing, what can we assume that value is? Well, that value being right here says that we are going to pass through the x-intercept. And even better, your leading coefficient here is what? Well, your leading coefficient, your A typically is out here. That would be whether it was a GCF that came out, or if it was a negative that got factor out, that would be located out right here. Excuse me. Now, because there is no negative, we can assume that these are now a parabola just facing up. If it was negative, we're a downwards facing parabola. And if we want, we could expand it. We could find where now x is equal to 0 and so forth, right? We are an upwards facing parabola. And if I changed it ever so slightly, let's say this had a degree of 2. We said if it's a degree of 2, we would bounce over the x-intercept. So for us, if we were to bounce at 2 and maintain, right, that we have a positive leading coefficient, well, 1 plus 2 means we have a degree here of 3. So that being an S-shaped curve. So for us to keep that S-shaped curve, right, we've come down. I have no other zeros other than the 1 here at 2. And we said we're going to bounce, so we're going to bounce right off and skyrocket up. And this is taking on still that S-shaped curve we've talked about, and you'll have that bounce to allow us to keep the S curve. So that's what multiplicities do for us if you do see them when you're factoring. Now for this one, when we factor, right, there's 4 terms. We're going to factor by grouping. So we can pull out an x. Well, first set equal to 0. X squared, x plus 2. We'll put out a -9 and leave behind an x plus 2. Don't forget a sign change. We have x squared minus 9 and an x plus 2. Keep factoring. X squared minus 9 is the difference of squares. So we have x minus 3 and x plus 3 and x plus 2. If you don't know how to factor, please go back to chapter 1.3. So now that you have all of your x-intercepts or all of your factored form, we can set each one equal to 0 and then solve. So we can add 3, subtract 3, subtract 2. So we have x is equal to 3, x is equal to -3, and x is equal to -2. These are your solutions, your x-intercepts. So again, if I'm going to put this really quickly on my graph, there we go. Come on. 1, 2, 3, 4. 1, 2, 3, 4. I have a positive 3.0. I have a negative 3.0, and I have a -2. So what is the shape of this graph? Well, the shape, right, is coming from the degree. So we should have some sort of S-shaped curve. And it's positive, your leading coefficient is positive. So we should, if we were to graph this, go up, down, and your -18 is your y intercept. So it should drop down quite a bit and then continue up. So that S-shaped curve is still there. You just have a few turning points in the way. And again, your multiplicities here, if we were to call them out, would be located here on the very top. Because we don't see them, we can assume that these are just ones. So all of your x-intercepts are going to pass straight through. So now let's see what we have when it's a little different. So we'll actually graph some of, we're going to actually get to graph these in a bit. So again, step by step. So first one, make sure that it's factored. Set it equal to 0. Plot your solutions or your x-intercepts. Determine the concavity or the direction with your end behavior. So kind of getting that mental picture. What is this going to look like? And then find additional points if needed. So for us, when it says graph the functions using the x and y intercepts, I'm also going to ask that you graph some in between points as long as they come out nicely. So when we look at this, it's already in factored form. So we don't need to factor it. All we need to do is set it equal to 0, -x, 2x plus 1, and x minus 2. We can pick out each and every one. So trying to find your x-intercept here, we set -x equal to 0, 2x plus 1 is equal to 0, and x minus 2 is equal to 0. So your x is at 0, your x is at -1/2, and your x is at 2. These are your x-intercepts. 0, 0, -1/2, 0, 2, 0. Now it does ask you to graph your y-intercept as well. Now, how do we find your y-intercept? Now, sometimes you may have already found your y-intercept. Anytime your x value is 0, we have your y-intercept. So we found it here, but let's say we didn't. For your x-intercept, we plug y in for 0 or f of x in for 0. For your y-intercept, we plug x in for 0. So in doing so, when we plug in a 0 into your equation, -0 times 2 times 0, so that's 0, plus 1 times 0 minus 2, right? It doesn't really matter because we are multiplying this whole thing by 0. So that's why this one comes up. But anytime we do try and find your y-intercept, we plug in a 0 for your x. So now let's go ahead and plug those points in onto your graph. So we have 0, 0 here. We have 1/2 or -1/2. So that's going to be right here, kind of hard to graph. And 2. So before we just start to connect these values, we want to, again, make sure that we look at your multiplicities. So your multiplicities here being right on top. And when we look at your multiplicities, we can also tell, okay, well, these are all going to pass straight through. x-axis. So because they're a degree of 1, they're all going to pass straight through your x-axis. And even better, when we count up all of your multiplicities, we can figure out the degree. So your degree here, 1 plus 1 plus 1 is 3. So we have a degree of 3. Your leading coefficient here, if we really expanded this out, we're really multiplying these first terms together, is a -2. So the -2 tells us that we are going to go down, and your degree tells us the shape. So we're going to be an S-shaped curve that goes down. So your end behavior, we're going to first start up high and then go down low. So we're going to go, oh, I keep messing that up. We're going to start up high and then go low. So we'll put that for your end behavior. So at the ends of your graphs, taking your last 2 points and suggesting that this is where they branch off. So again, this one should go high and this one should go low. Now, when it comes to some of these values here, what I would like you to get the hang of is finding your in-between values. And I'll be nice as long as I won't make you find, let's see, find, what are these called? Fractions. So as long as your solution comes out nicely, so notice that we have 0, 0 here and 2, 0 here. I'd like you to find an in-between value. And this goes for any value or any solution where you have some in-between space, some gaps. So to find the gap, find the in-between, find the in-between point, right? Well, what is a nice number between 0 and 2? Well, that's going to be the point 1. So let's go ahead and graph or find when x is equal to 1. And we get to plug that right into your function. -x, 2 times 1, or 2 times 2x plus 1, x minus 2. So we get to plug 1 into your graph. 2 times 1 is 2, plus 1, minus 1. So you have -1 times -1, so it's really a positive 3. So we have the coordinate 1, 3. So on here, we're going to graph 1, 3 all the way up here. And then from here, we're just going to connect your dots. Again, I won't make you graph a fraction in case we have it. So we can suggest that this comes down, goes back up, touches this point up here, and comes right back down. Now for in-between points, if you had more gaps, the more x-intercepts you have, the more in-between points I would like you to find. Again, as long as the points come out nicely. And it only has to be 1 point between those two solutions, those two x-intercepts. Now let's have you pause the video and try it again with B. So step 1, set it equal to 0. Step 2, factor. Again, if you don't know how to factor, please go back. Our goal today is not to know how to factor, or like our lecture is not on factoring itself. So we're going to skip that lesson on factoring. You need to go all the way back to 3.1. Now we get to go ahead and set each equal to 0. So x is equal to -3 and x is equal to 1. These are your x-intercepts at -3, 0, and 1, 0. Again, this is where your y is equal to 0. And for your y-intercept, your y-intercept is when x is 0. So if we were to plug in a 0 into either your original or your factored form, it doesn't matter. G of 0 is equal to 0 squared plus 2 times 0 minus 3. So therefore it's -3. It's nice to do it into your expanded form because it's always going to be your constant there. If you plug it into this form, you would have to plug x in for 0, and then 3 times -1 is just -3. So we have we have 0, -3. So let's go ahead and plug these points in. And then if we need more in between points, we can certainly get one. So we have, let's see, -3, 1, 2, 3 right here. Go to this blue. You have 1 right here. And then we have -3 down here. Now let's take a look at the direction of your graph. Well, the degree here is 2. Your leading coefficient here is a +1. So we're going to be an upwards facing parabola. And because between these 2 points, right, between -3 and 1, we could have chosen any point to have, but we already have one of your values here. So we can just go ahead and connect your dots, knowing that for your end behavior, right, we are going to go up on either ends and then graph like this. Now, because this is a quadratic, you could also apply what you know about your quadratic functions. So you could still find your vertex if you'd like. You could always find some of your other points as well. So definitely use what you know in your arsenal when it comes to graphing quadratics. For us, you didn't need to, like I just asked for one in between point. We have your y-intercept. Let's say you did want to graph your vertex here. X is equal to -b over 2a. That would be -2 over 2 times 1, so -1. So if we plug in a -1 into, I'll say even your factored form, -1 plus 3, -1 minus 1. So that's -2 times 2. So that gives us -4. So we have the vertex, -1, -4. So again, that is if you wanted to graph using your vertex as well. This being your lowest point right here. Oh, wrong point, right there. So if you needed an extra in between point. Let's have you graph one more. All right, so when it's in this form, right, we could do one of two things if we're trying to factor. So if you wanted to take the factoring approach, keep in mind, we talked about how to factor when it looks like a quadratic-like problem. We can rewrite your x to the 4th as x squared minus 1. Do you remember these? Perhaps? Right? And this is even a special one because this is a difference of squares. It's just kind of hidden in the mix. We said with your difference of squares, right, we really have two of these x squares now. We have -1 and +1. So for your factored form, we have x squared minus 1 and x squared plus 1. And if we were to expand this, we have x plus 1, x minus 1, and an x squared plus 1. So these are all of your factored forms. Now, when we go to find your solutions, we can set these equal to 0. So you get x is equal to -1, x is equal to 1, and x is equal to plus or minus the square root of -1. Now, this is a non-real solution. If we did have more times, we could show you a little bit more as to how to graph these. This is kind of just going to give us like a little blip, a little like not cusp, what are these called? Like a little corner, or no, it is a cusp, a little cusp at your graph here at, however, excuse me, we're not graphing these real solutions. So these are the only two that we would go ahead and graph. So these are your x-intercepts. We have -1, 0, and 1, 0. Your y-intercept here This is when x is 0. So if we plug in a 0 in for your x value, we get out a -1. So 0, -1. Let's go ahead and graph those. And that is acting, that y-intercept is acting as your in-between point. So we don't need to pick any other points. We do want to know your degree. So the degree here is for your leading coefficient is +1. So we are usually this U shape, or if you have a lot more to it, it could be that W shape to it. But your end behavior here is going to be going upwards. And we can just connect. Now, if we approach this from a transformation standpoint, we're taking your graph f of x to the 4th. So we're taking your graph here, and we have translated it, we have transformed it by going down 1. So go down 1. So sometimes if it works, if it's kind of a nice variation, you don't have to use such a complicated method. Instead, you can use what we've learned from chapter 4.1 about transformations, moving your graph up, down, left, right, and any sort of reflection. Now, I will ask that you continue on with this video and watch the next video on how to graph a few more of these polynomials, because there are so many different things to graph. Keep in mind, if we've changed a couple of these problems, we could always try it with different multiplicities should we want.